Today we're going to go over a new idea on the unit circle. This is for Unit 11 and it covers the unit circle, radians and degrees, and Pythagorean identities. I think at first glance, if you've not seen the unit circle before, it can look a little bit intimidating because there's so much information on the unit circle. I'm going to do the best I can to break this down so that you can see what all this information really tells us. So the unit circle is divided into sections on the coordinate plane. This is quadrant 1, this is quadrant 2, here's quadrant 3, and then here's quadrant 4. These are labeled in degrees here. So this line represents 30 degrees from the x-axis, where the x-axis represents 0 degrees. Each of these points on the circle are coordinates. Our coordinates, of course, are x comma y, and those coordinates tell us the value of cosine and sine, where x is cosine and y is sine. Our circle also goes counterclockwise, so it might seem a little backwards to you. A clock ticks, a clock ticks this direction, but our unit circle, when we're talking about things in trigonometry, it goes this direction. It goes counterclockwise. Another thing about the unit circle is that the radius, which is all of these lines that are going out from the center and extending to the outer edge of the circle, the radius is equal to 1. So that equals 1. Now we've talked about how this is 30 degrees here, but this can also be represented in radians. And this is pi over 6 radians is equal to 30 degrees. A nice conversion is that pi radians equals 180 degrees. I think that's probably the most helpful one on here to know how to make those conversions. And we'll go over how to do some example problems together also. So the reason that we have sine and cosine is because we can start to look at uh, a proof of how sine and cosine exists as these coordinates. So let's look at a quick example here. If we make this into a triangle, this becomes a right triangle. Now our right triangle is the base of that triangle is the x coordinate, or root 3 over 2. I'm just going to write that as x equals root 3 over 2. And the y coordinate is 1/2, or our triangle is 1/2 of a unit tall. And the radius is 1. The radius is always going to be 1. And this might be review for you from geometry with sine, cosine, and tangent. When we solve for these trigonometric ratios, we use the acronym SOHCAHTOA. So to find sine, that equals the opposite side over the hypotenuse. For cosine is equal to the adjacent over hypotenuse. And for tangent, it's equal to the opposite over the adjacent. And so we can prove that sine 30 is equal to y. And we can check that on our calculator. So if we type in sine 30, actually let's write it like this first. So we're going to check our angle. We know our angle is 30 degrees. And we're going to prove that y equals 1/2. So if we just say that that equals y, we would say sine 30 is equal to the side opposite of the angle, which is y, over the hypotenuse, and hypotenuse is 1. So this says sine 30 is equal to y. Now, if you have your calculator set to degrees, you can type sine 30 in your calculator. Sine 30, and it will give you exactly 0.5. And so that's just a quick proof on how we get these numbers. So sine is 1/2 for 30 degrees. Just kind of a side note, so we talked about sine and cosine on these coordinates. You can calculate tangent as well. And tangent, and a shortcut for tangent is, move this out of the way here. Shortcut for tangent is, if we wanted to find tangent of 30 degrees, that would be sine over cosine, or y over x. And so the opposite over the adjacent. So for 30 degrees, the opposite is y, and then the adjacent is the side next to it that is not the hypotenuse. And so the adjacent would be √3/2. So to find tangent of 30 degrees, for that, we know y is 1/2, and we know x is √3/2. And then we would rationalize the denominator, and we would just multiply by 2 over √3, 2 over √3. That becomes 1 on the denominator of our complex fraction. Then we get 2 over 2√3, and then we would times by √3/√3. And I'm just showing you some basic calculations of what we would do to rationalize the denominator and get rid of the square roots. That's what this last part is. And so we get square root of 3. And we can check that on our calculator. We can type tangent of 30, and we get a decimal of 0.577. Then you can also type square root of 3, and looks like that's not correct. So let's go back and take a look and see what happened here. So tangent of 30 is 1/2 over √3/2. Let's see what happened here. So we canceled out our denominator there. We have 2 over 2√3, and we multiply by √3. I see what happened here. So I made a small mistake here. This was supposed to be 2 times now √3 times √3. I made that cancel out. You're not supposed to do that. That's actually, the square roots cancel out, and we're left with the 3 on the bottom. So this is 2√3/6, which is √3/2 divided by 6. That would make that 1/3. So we did √3/3. Now we would get 1.732 for √3 divided by 3 is 0.577. Okay, that's a little bit off topic, but I just wanted to show you how we calculate what tangent is and how we rationalize the denominator. And that mistake that I made earlier was √3 times √3. Square roots should have canceled out and given us a 3. I made the entire thing go away, and that's not correct. Okay, let's take a look at some of these practice problems now. Now that we know some basic information on the unit circle. So here we have our unit circle. We have these points A, B, and C listed here. And we want to find out which of these 3 coordinates equals cosine of 50. And actually, let's copy our unit circle here, just so we can kind of get a reference point for this first one. So cosine of 50 degrees is going to be about here. And that looks like it's point A. So we can cross out answer choice C and D. Those aren't right. It's not going to be point B. Point C isn't even on there. And now it says, which one's cosine of 50? Well, cosine relates to the x coordinates. So it's going to be the x coordinate of point A. Let's try another one without, uh, the unit circle. Try this next example here. It says for each point on the unit circle, select the angle that corresponds to it. And these are all of our selections for all three of these points. So 45 degrees, we can separate these into chunks. I think that might be a little easier. So this is 90 degrees, this is 180 degrees, and this is 270 degrees. And then this would be 0 and also 360 degrees. So now we can see this a little bit easier without having to go back to the unit circle. So 45 degrees is between 0 and 90. So that probably might be A. Let's write that for now, and we can change it if we need to. For B, looks like it's greater than 180 degrees, but less than 270 degrees. And our only answer choice for that would be 225 degrees for B. So write 225 degrees for B. And then for C would be greater than 270 degrees and less than 360 degrees. So that would be 315 degrees. Okay, let's try a couple more of these. Same kind of question as number one. We have A, B, and C on the circle, and we want to know which coordinate is equal to sine of 90. 90 degrees is here, so it's going to be coordinate A. You can cross out these answer choices. And it wants to know sine of 90, and sine corresponds to the y coordinate. So it's going to be the y coordinate of A. Okay, this next example has a lot more answer choices to look at. It says, what's the value of the x coordinate of point A? And it says 50 degrees here. That doesn't mean that it's 50 degrees. That means that that's called a reference angle, and it's in reference to 180 degrees. So this 50 degrees means that it's 180 degrees plus 50 degrees, which is a total of 230 degrees. And if we wanted to write that entire angle on the coordinate plane, we would write the angle like this. We would show that it's like that. And usually we call angles theta. We sometimes call them alpha as well, instead of using letters like x or y, because x corresponds to cosine and y corresponds to sine. So this says, what's the value of the x coordinate of point A? So we're looking for something at 230 degrees. So this would be the x coordinate of point A would be cosine of 230 degrees. All right, next we're going to look at radians and degrees. So for this next problem, we want to convert these radians into degrees. And I have a unit circle here for our reference. And the best way to do this, well, there's two ways to do it. I'm going to show you the long way first, and then I'll show you the shortcut method for this. So we're going to start with what we have and what we're given. We're given 5 pi over 12. And if we look at the unit circle, it looks like they don't give us that on the unit circle. So that's okay. We can still change this into degrees. We're going to write this as a ratio. We're going to say 5 pi over 12 radians times, now we're just going to multiply by a ratio that is equal to 1, which is 180 degrees over pi radians. And really, these are radians also up here. Now, our radians are on the top of our fraction to start with, and then we're multiplying by something that equals 1. This equals 1. Those are the same thing. And so the radians cancel with the radians, pi cancels with pi, and then we just have 5 times 180, which is 900. And we're going to divide that by 12 because that's just 12 times 1 now on the denominator, and we get 75 degrees. Okay, so if you're going from radians to degrees, you multiply by, let's write this down, radians to degrees. You're going to multiply by 180 over pi. If you're going from degrees to radians, you're going to multiply by pi over 180. So that's how you can cancel out the pi and you'll just be left with degrees. This next example is fairly straightforward. It says convert this angle 180 degrees to radians. So we're going degrees to radians. We're just going to multiply by pi over 180. So we write what we're starting with. 180 times pi over 180. And that cancels out very nicely. And we're just left with pi radians. Or we just write pi for our answer there. It has radians as the units. Okay, the next one's a little bit tougher. 17 pi over 18. We can estimate on the unit circle if we want to. This is very close to just 1 pi, so very close to 180 degrees. So we can estimate that it's right there if we wanted to make an estimation. Now I'm going to show you the quicker way to do this. Instead of doing 180 over pi, you can directly just plug in 180 degrees for pi. So you can say 17 times 180 over 18. And this is the shortcut method for converting degrees, or excuse me, radians to degrees. 17 times 180 is 3060, and we're going to divide that by 18. And we get 170 degrees. So that's our shortcut method for these. Okay, the next one wants us to go to radians. So 70 degrees to radians. And if you're not sure ever which goes on top or bottom in terms of pi or the 180 for these conversions, you can just ask yourself, well, ask yourself, what did we start with? So if we started with degrees, then we're going to put degrees on the denominator. So that way they cancel out. So we get 70 pi over 180, and that's 7 pi over 18, and that looks like that's all we can do to simplify that one. All right, now we're going to take a look at the unit circle with radians. And this is very similar to what we did earlier when we were looking at where's point A located or what are the points A, B, and C in terms of degrees, except now they're just in radians. And so I would say the easiest way to do these would be, first of all, use our shortcut that pi is equal to 180 degrees. And just change all of these into degrees. So if we take a look at A is between 90 degrees and 180 degrees. Take a look at B, it's between 180 degrees and 270 degrees. And C is between 270 degrees and 360 degrees. And we can also write this in terms of pi if we wanted to. So we could say A is between pi over 2 and pi. B is between pi and 3 pi over 2. And C is between 3 pi over 2 and 2 pi. So these all go up by 1/2 pi. Pi over 2 is the same thing as 1/2 pi. And so if we have 1 pi plus 1/2 pi, we get 1.5 pi, or 3 pi over 2. This last one's 2 pi at 360. So maybe that might help you with the estimations. If it's easier for you to look at the unit circle and just take a screenshot of the unit circle, you can take a screenshot of that, and that might be able to help you with some of these also. So let's go back to this problem now. So that's where A, B, and C is between, and now we got to check these different answer choices. So pi over 3 is 1/3 pi. I'm just going to change all these into degrees. That's always been easier for me. So our first answer choice is pi over 3, which equals 180 over 3, which equals 60 degrees. Our second answer choice, 3 pi over 4, is 3 times 180 over 4, which equals 540 over 4, which is 135 degrees. 9 pi over 7, 9 times 180 over 7, which gives us 1,620 over 7. And that's about 231.42 degrees. Now, the reason we use radians is to be very exact with degrees. I put about for this because it's just an estimate out to the hundredths place. So that's why we use radians instead of degrees a lot of times. And then our last one is 11 pi over 6. It's 11 times 180 over 6 is 1,980 over 6 is 330 degrees. Okay, now we can match these up using this this logic here. So A is between 90 and 180. We're just going to check to see which one that would be. Looks like this would give us A, 135 degrees, or 3 pi over 4. For B is between 180 degrees and 270 degrees. Looks like the only one is the 231.42, or 9 pi over 7 answer. And for C is between 270 and 360. Looks like this one's what C is. 11 pi over 6. All right. So we'll do one more problem like this, just maybe a little bit more quickly for our next example. It says, again, select the angle that corresponds to it. So pi over 6 is 180 over 6. And that's equal to, it's equal to 30 degrees. 8 pi over 7. It's 8 times 180 over 7. That's 1,440 over 7, or about 205.71 degrees. 7 pi over 5 is 7 times 180 over 5, which is 1,260 over 5, which is 252 degrees. Get a whole number for that one. And then 5 pi over 3 is 5 times 180 over 3, or 900 over 3, which is 300 degrees. Okay, let's try to make some sense of what our answers are telling us. So for A, it's less than 90 degrees. Because 90 degrees is here, or pi over 2. So this one's gotta be A. Pi over 6 is A. For B, it is greater than 180, less than 270. So it looks like for B, it could be either one of these because both of those are greater than 180 and less than 270. So now we've got to make sense of, is it closer to 180 or closer to 270? And it looks like it's closer to 180 degrees than 270 degrees. So it looks like this one's going to be what B is, 8 pi over 7. Let's circle these here. And then for C, greater than 270 degrees, less than 360 degrees. That just leaves us with 5 pi over 3 or 300 degrees. It's our only option there because 252 is less than 270. All right, the next part is the Pythagorean identity. And here I just showed us a quick example of the unit circle using just the quadrants and the 90, 180, 270, and 360 degree marks on there. Notice also that these are nice numbers, 0, 1 for 90 degrees, negative 1, 0 for 180 degrees, because the radius is always equal to 1. We're going to use the fact that the radius is equal to 1 in order to prove the Pythagorean identity. And the Pythagorean identity is basically just the Pythagorean theorem, but we're proving that it works on the unit circle, and we're proving that it works anywhere on the unit circle. Let me show you what I mean by that. If we have an angle from here to here, and we'll call that our angle theta, this point represents cosine of theta, sine of theta. Earlier, I just simplified it. I said it's cosine and sine, but really it's cosine of theta and sine of theta. Now, if we draw this triangle like this, and this makes a right triangle, we can say that from here to here is x, and from here to here is y. We also know that the radius of our unit circle is always equal to 1. Doesn't matter what angle we go out by, as long as it's from the center to the outside, the radius equals 1. So our Pythagorean theorem tells us this. If we look at let's look at a similar triangle. I think this might be review for you once you see this. The Pythagorean theorem says, write this out here. Pythagorean. The Pythagorean theorem says a squared plus b squared is equal to c squared. So what that means is leg 1 and leg 2, if we square those, that equals the hypotenuse. Leg 1 and leg 2 can always be flipped around, doesn't matter. But c is always the hypotenuse. This is what the Pythagorean theorem is. And if we know two sides of a triangle, of a right triangle, we can find the third side algebraically with the Pythagorean theorem. So you've probably seen the Pythagorean theorem with a squared, b squared, and c squared. But now we're going to look at it with x's and y's and cosine instead. So let me get rid of this and we'll see if we can sort of simplify the Pythagorean theorem in terms of x's and y's. So instead of a squared, I'm just going to actually just rewrite this up here. Equals c squared. Instead of a squared plus b squared is c squared, we're going to say x squared plus y squared equals 1 squared. 1 is what c is, and if we square it, it's 1 squared. So now we have x squared plus y squared is equal to 1, because 1 times 1, or 1 squared, is just 1. Now we said earlier that cosine of theta relates to x and sine of theta relates to y. So cosine squared theta plus sine squared theta is equal to 1. This is what's called the Pythagorean identity. So this was the Pythagorean theorem. This is the Pythagorean identity. And that's what we're going to be using with all of these problems. Now, I'm showing you the Pythagorean identity here on quadrant 1. On quadrant 1, it makes sense intuitively. We can see, yes, A matches with X, B matches with Y, and we have a nice triangle. But that's not always the case. And I'm going to show you our first example where it's not. It's a little bit different. So actually, before we get to that, let me just show you this before we even get to an example. So depending on our quadrants, our cosine and our sine changes. So if we have something here and we have our triangle like that, our cosine, our x, ends up being, our x coordinate is positive. We have a positive x coordinate and a positive y coordinate. That's if it's there. If it's in quadrant 2, somewhere over here, and we make a triangle over here in quadrant 2, now our x coordinate is negative and our y coordinate is positive. And that's what this table shows us. You might want to take a screenshot of this table to help you with our problems that we're going to work on. If we have quadrant 3, if we had something here, our x coordinate's negative and our y coordinate's negative. And that's what those two negatives tell us there for quadrant 3. And then for quadrant 4, our x coordinate's going to be positive and our y coordinate's going to be negative. Make a triangle like that. Okay, so we're going to be using reference angles for angles that are bigger than, or we're going to use reference angles for some of these. Let me just simplify it and say that. So here's our first example. It says this angle is in quadrant 3. We know sine of that angle is equal to negative root 3 over 2. Find what cosine of the angle is. Now let's draw this out so we can kind of make sense of what's happening here. We're going to use the Pythagorean identity. So we're going to use x squared plus y squared equals 1 squared, or cosine squared theta plus sine squared theta equals 1 squared. We're going to use that, but when we get our final answer, we have to decide by using this table here, is our answer going to be positive or negative? So we got to use this table to find that out at the very last step. And to show you what the table means a little bit better, we're going to use the coordinate plane. We're just going to sketch where this would be. So it says, first of all, we're in quadrant 3, and we have an angle in quadrant 3. So I'm just going to draw our line like that. And we've got an angle theta right there. So it's going from 0 and extending to quadrant 3. And we know that our coordinate is x, comma, negative root 3 over 2. That's what our coordinate is of this point. Now if we draw our triangle, you just get rid of this 3 from quadrant 3, or just move it over here. If we draw our triangle now, we know our radius is 1. We know that from here to here is negative root 3 over 2. And we want to find what x is. We want to find that x value there. So let's take a look at the Pythagorean identity. Let's plug these numbers in. So cosine squared theta plus sine squared theta is, we know sine theta is negative root 3 over 2, and we're going to square that. And that equals 1 squared, or just 1. Cosine squared theta plus, now this becomes negative square root of 3 squared over 2 squared. We're squaring both the top and the bottom. And this becomes 3/4. It's equal to 1. We're going to subtract by 3/4 on both sides. You get cosine squared theta equals 1 minus 3/4 is same thing as 4/4 minus 3/4, which is just 1/4. And now we're going to take the square root of both sides. And we get cosine of theta is equal to plus or minus 1/2. Because the square root of 1/4 is the square root of 1 over the square root of 4, which is 1 over 2. And because we took the square root, we're doing plus or minus for our answer. Okay, now let's go back to this diagram that we have here. We're in quadrant 3. Cosine means x. So because cosine is x and we're in quadrant 3, x is negative in quadrant 3. X is always negative in quadrant 3. And so our answer for x, or our answer for cosine theta, is only the negative answer. So negative 1/2 is what cosine of theta is. And we can check that on our table. Let me see if I can go back to our table here. We're in quadrant 3. We want to find what cosine is for quadrant 3. And it is the negative value. So the reason that I was drawing out our diagram like this is so that you could make sense of what the table even means. So you don't have to draw a diagram for each one of these, but just make note of the fact that we have to determine what quadrant that it's in to figure out what the value is, if it's going to be a positive value or if it's going to be a negative value. So it's not, excuse me, that's supposed to be negative 1/2, not positive 1/2. Okay. Let's take a look at, maybe we'll do just a couple more of these, maybe just do one more of these ones. So this says the angle is located in quadrant 2 now. And if we say that's in quadrant 2, that's this quadrant here. So here's our angle, like that. And if we draw our triangle, we know cosine of the angle is negative 12 over 19. So we have negative 12 over 19, comma something, or comma y is where that point is. And we want to find out what y equals. So we're going to use the Pythagorean identity again. Cosine squared theta plus sine squared theta equals 1 squared. And so this is negative 12 over 19 squared plus sine squared theta equals 1. And this becomes, let's see here, this equals 144 over 361 plus sine squared theta equals 1. We're going to subtract that. Get sine squared theta equals, now 1 minus this make sure to keep this as a fraction. We're going to change this 1 to 361 over 361. This is very important. If you try to do this as a decimal, it's going to not give you the exact answer. Because these all want you to answer the the answer in exact form. So over 361 sine squared theta equals 361 minus 144 is 217 over 361. Now we're going to take the square root of both sides, and we get sine theta equals 217, square root of 217 over 361. Okay, now square root of 361 just so happens to be 19. So this actually is, should wrote plus or minus there also. So square root of 217 over 19 plus or minus. Now let's take a look at what quadrant we're in. We're in quadrant 2. And for y is always positive in quadrant 2. And so we're just taking the positive answer of this. So our final answer should just be the positive amount. So it's positive root 217 over 19. Again, let's take a look at the sign chart for the quadrants. So we're looking at sine quadrant 2 is positive. And again, if you haven't taken a screenshot of that, make sure that you have a screenshot. That'll help you with these problems. Okay, the last part of this is figuring out trigonometric values and expressing them exactly. So find our next problem. These are called trig values of special angles. Now, it wants us to find cosine of 150 degrees and sine of 150 degrees. Some of these you can identify immediately from the unit circle, like this one. Cosine of 150 is negative root 3 over 2. Sine of 150 is 1/2. Now, if you type these in your calculator, you will get the decimal amount, but it doesn't want you to type the decimal amount. It wants you to type the exact answer, which is in radical form as a square root. So you can use the unit circle for this one. Let's see what we would get. Let's see how to solve this without the unit circle. Let's see if maybe we can go to the next one without the unit circle. Actually, let's solve this one without the unit circle. So if we wanted to sketch this without the unit circle, we would find 150 degrees. So we'd sketch about where it's located. We'd draw our angle, 150 degrees. We would also draw our triangle. And now we have to figure out, what is this angle here? Well, it's 30 more degrees to get to 180 degrees. And we know this is x, this is y, we know that's 1. And so now we can figure out, well, what is sine of 30 degrees? Sine of 30 degrees is opposite over hypotenuse, or y over 1. So that's what our y is equal to. And sine of 30, if we check here on these first 3 points in quadrant 1, if you memorize these first values, they go in a specific order around the unit circle. So the pattern continues. So if you know these, that's going to help you to solve these larger values. So if you can memorize that sine 30 is 1/2, then you'll know that that is equal to what y is. So now we know that because sine 30 is 1/2, that sine 150 is equal to 1/2. So we also have to use our sign chart to make sure that it's positive 1/2 and not negative 1/2. Y is positive in quadrant 2, so sine is positive, so we do get 1/2. Now, if we wanted to check cosine, cosine of 30 is equal to adjacent over hypotenuse, or x over 1. So cosine of 30 is equal to, let's see here. So cosine of 30 is equal to, we're going to look at cosine now. That's root 3 over 2. And therefore, cosine of 150 is also equal to root 3 over 2, but we're in the quadrant 2, and x is negative in quadrant 2. It's quadrant 2. X is a negative value always in quadrant 2. And so we're going to get negative root 3 over 2. So that's how you can simplify these larger angles into smaller ones. If you can memorize the order of 30 degrees, 45 degrees, 60 degrees, you can separate these into smaller chunks. Sine starts at 1/2, it increases. Sine goes up as we go up. Cosine starts larger and it decreases as we go up. All right. Looks like we have time for one more problem here. Let's go over one more together. This says find the following trigonometric values. The first thing I would do for this is convert 7 pi over 4 into degrees. That's 7 times 180 over 4. And that's 1,260 over 4, which is 315 degrees. So now we can make a quick sketch of where 315 degrees is. And say maybe it's about there. And our angle would look something like that. If we draw out our triangle, put the 315 degrees actually. 315 degrees is our angle there. And then what's left over is 360 minus 315 degrees, which is 45 degrees. So again, if we look at our unit circle in the beginning of our unit circle, it goes for sine, it starts small and it goes larger. And for cosine, starts larger, gets smaller. And this is for 30 degrees, this is 45 degrees, and this is 60 degrees. And we want to know for 45 degrees, so we're going to find cosine of 45 degrees is root 2 over 2. Therefore, cosine of 7 pi over 4, or 315 degrees, the x is positive in quadrant 4, and so we still get root 2 over 2 for 315 degrees. Now, sine of 45 degrees is root 2 over 2. And y is negative in quadrant 4. And so sine of 315 degrees is negative root 2 over 2. So this cosine, 7 pi over 4, is the same thing as 315 degrees. We get root 2 over 2. And the sine of 7 pi over 4 is negative root 2 over 2. So hopefully that was helpful for learning about an overview of the unit circle, as well as how to make some conversions and to simplify different parts of the unit circle, and to find what these angles are by using smaller angle measure values. That's everything for quiz 1 on unit 11.